Now we know how to make haloalkanes or halogenoalkanes, we can use the terms interchangeably, we can start to see what they can do themselves. Generally, when we're making haloalkanes, they are a step along a pathway to a molecule that may have a different functionality, usually alcohols or carboxylic acids or other things like that. So with the addition of the halogen, alkanes become more reactive, which makes sense because we've gone from having all these non-polar bonds to now having a highly electronegative halogen attached to our carbon. This means that it has a polar bond and it's going to make our central carbon, this black one here, a little bit positively charged. So it's got a permanent dipole in it. We tend to refer to the carbon that has the partial positive charge as being electron deficient because the halogen will be holding on to the electrons in the bond more often. And then the halogen is electron rich. So this central carbon atom in all of these is known to be electron deficient. With the presence of the halogen, what this means is that that halogen is a little bit more primed to be able to take both the electrons from the bond and form an anion, leaving the carbon free for a new group to come in. So because the bonds between the halogen and the carbon are polar, then it means that that bond is more reactive. There are ways in which we can break it and cause a new compound to be formed. We can see here in this OH minus here, so this would be a hydroxide ion, it'll be attracted to the partial positive on this carbon. Okay, so the partial positive on this carbon here will be attracted to the negative. This lone pair of electrons can come in. The arrow shows the movement of 2 electrons. You can notice it has a double-headed arrow rather than a fishhook that we saw with the radical mechanism. So in this case, the OH minus attacks the partially positive, pushing the bonds from this bond out onto the chlorine, forming a chlorine anion, and we form the new alcohol. So the kinds of things that can attack this partially positive carbon are known as nucleophiles. This is nucleus loving, and if you remember, the nucleus is a positively charged part of the atom. So this means usually electron-rich species. So for a nucleophilic substitution reaction, we're going to have something that has a lone pair of electrons or a negative charge that has an electron-rich species that can attack that positive charge and push out our halogen in a substitution reaction. By definition, again, remembering we have to know our definitions, a nucleophile is an electron-rich species that is attracted to parts of molecules that are electron deficient. So the hydroxide ion that we saw in the previous example is an example of a good nucleophile. It has lots of electron pairs and an extra negative charge. So we can see this common reaction between sodium hydroxide or any strong base, so it could be potassium hydroxide, sodium hydroxide, anything that's going to release OH minus into solution will act as a good nucleophile. When this attacks chloromethane, perhaps, we will get methanol, or it could even attack bromopropane and form propanol. The position of the halogen gives us the position of the alcohol. So in this case, it would be propan-1-ol. Because it's a substitution, we need to remember that we will get more than one product because the chlorine is going to be kicked out. And you can see here that we're going to form the salt, NaCl, or sodium bromide as well here. Okay, so unlike an addition reaction, we get the product that we're after plus a side product that is usually the ejected halogen and the salt, the cation from the strong base that was used. Nucleophilic substitution reactions, we will learn the mechanisms in higher level, but for standard level you just need to know that a nucleophile is an electron-rich species that is attracted to the partially positive carbon in a chloro or a halogeno-substituted alkane. This moves the electrons, it breaks the bond to the electronegative element, the leaving group, and forms a new bond between the nucleophile and the carbon. You can see here, this is the example with chloroethane, that we have chlorine plus a hydroxide ion goes to CH3CH2OH, so our ethanol plus the chloride anion. I want you to pause the video, think about some of the nucleophiles that we saw a couple of slides back, and what other classes of compounds could we possibly make during these. By reacting with strong bases, we can get alcohols, but what other nucleophiles might we commonly see? Hopefully you had a bit of a think and you went back and looked at them. A couple of common ones that we're going to look at is the addition of ammonia. Okay, because remember with ammonia, the nitrogen has the lone pair, so it has the potential to act as a nucleophile. The other one that is quite common is water. Again, remembering that water has those two lone pairs on the oxygen, which makes it quite a good nucleophile. You may have also thought about the cyanide anion or a number of the others. These can also form nitriles and other families of compounds. Let's look at water. So when we look at this, the hydroxide ion is the easiest way to do this, and we look at the RClOH going to ROH, which is our alcohol group. The other substitution reaction they can undergo is with water to form an alcohol. With this, we do need a catalyst present, whereas we didn't with the strong base with the hydroxide. So it needs a catalyst present, and our byproduct this time is going to be HCl, because we're going to add in the OH from the water onto our molecule, leaving us with a hydrogen and the chlorine that is pushed out of the molecule. So we're going to end up with HCl as our byproduct. So in this case, we could monitor pH to see how well the reaction has progressed, because we'll be generating an acid as it goes. But key thing to remember here is it does require a catalyst. So in most cases, you will actually see the reaction with the strong base being the one that we most commonly refer to using for the production of alcohols from haloalkanes. Another type of substitution we can look at is the amination, or which is looking at forming amines. Okay, so in this case, we're going to use ammonia, and the position of the halogen, again, much like the alcohols, will determine the position of the amine. So if we have chloroethane here, we can form the aminoethane compound here with this primary amine, because it's at the end of the chain. Or in this case, where we've got 2-chloropropane, the amine will attach to this 2 position, forming the secondary amine that we have here. Sorry, actually, this is still a primary amine. It's important with amines that the primary, secondary, and tertiary talks about the positions on the nitrogen. So in this case, we still have 2 hydrogens attached to the nitrogen, so it's still a primary amine, same as this one. To have a secondary amine, we would need to have 2 R groups with a single hydrogen coming off it, would be a secondary amine. Or in the case of a tertiary amine, we would have 3 R groups coming off the central nitrogen and no hydrogen at all, just like our primary, secondary, and tertiary alcohols.